So I'm Rudy Woodridge. I'm the Vice President of Engineering Services at IRIS. We're out of Sarasota, Florida. And I'm going to talk to why the heck do we need effective electrical maintenance programs? This seems kind of self-evident to electrical people, but for the rest of the world, it sometimes is a question mark. So virtually everything that we do in industrial process is run by electricity. There are a few exceptions. In the steel industry, they use gas as a primary fuel for melting different metal substances and so on. But even in that industry, electric arc furnaces are quite prevalent too, so it's kind of a mix. The only sector where we're not using electricity as our primary source of energy is currently transportation, but that's going to change too. So we have a revolution and evolution on our doorstep of migrating to a larger mix of electric vehicles than fossil fuel-based vehicles. Now, whether we like that or we don't like that, we agree with that migration or not, it's coming, and it's going to mean a lot of changes to the general electrical grid and the demands upon the grid as well. So generally speaking though, when electrical systems fail, everybody notices. We take it for granted that the lights are on, that the electric heat is running, that the motors are running, and then when it goes away, all hell breaks loose. And when these things fail, they can fail catastrophically as well. There's a lot of available fault energy there, and when something does fail, if we have an insulation breakdown and an arc to ground or a face-to-face fault, significant amounts of energy can be released, and there can be catastrophic consequences for the facility as well. The challenge with electrical systems is that I can't tell if it's working properly when it's off, right? Which one of these light bulbs might be defective? Don't know. I've got no way of testing necessarily that light bulb. Well, okay, maybe I could do a resistance test on it or something like that. But for the most part, our electrical assets, it's very difficult to tell what's happening unless we energize them. All or most of our condition-based techniques that we deploy to assess the health of our electrical assets require those assets to be energized at the time that we're performing the test. Right? So if I'm doing infrared, if I'm doing ultrasound, et cetera, most of these things I need to do with the equipment energized. There are some exceptions. There are some things that we can do de-energized. Transformer oil sampling is a good example of that. Doesn't matter, right? The transformer was on within the last, I don't know, days. It's probably fine to take an oil sample, okay? Visual inspection obviously can be done with the equipment de-energized. But for the most part, to get really good asset health data, we need to have those assets energized and running under what we would call a normal level of load. All right, and NETA has some guidelines about what normal is, and for how long that asset should have been running before we try to take the data. So if we're doing infrared, for instance, we need to have had that asset running for a certain period of time so it's reached thermal stability, that things have had a chance to warm up as they would under normal conditions. So what are the technologies? We have infrared, as I mentioned. It is probably the most prevalent technology deployed to assess the health of electrical assets. Why? Because the primary mode of failure of electrical equipment is heat. Yes, heat. Heat is the killer. Everything electrical hates heat. The second technology is ultrasound. Ultrasound allows us to listen for partial discharge type events which give off noise in the ultrasound spectrum above the range of human hearing. Humans can hear up to about 20 kilohertz when you're young. As you get older, that declines. So I'm at about 15, 16 kilohertz right now, and as I get older, it'll go lower and lower. It's the high frequency part of our hearing that we lose first. But ultrasound listens typically above 20 kilohertz, usually at around 40 kilohertz, but up to 100 kilohertz is the range that we're listening to. And electrical partial discharge events, arcing, tracking, and corona, all give off noise in the ultrasound spectrum. They all allow us to hear that, and they all look a little bit different. If we're able to capture that actual waveform, the different types of defects have a different signature pattern to them. All right, so with some software and some analytics, we can actually tell, is it arcing or is it tracking? Some people can tell if they've been at it long enough just by listening to that sound. I can't, right? We have guys that on our staff who can, but I can't do that. So I would rely more on the software side to say, okay, what does this look like in the time series? Can I break it down as a frequency domain plot? What frequencies am I seeing? What patterns am I seeing? Then I can tell what kind of issue it is. Partial discharge testing is a little different. So when I talk about arcing, tracking, and corona, those are all partial discharges, but those are partial discharges directly into air, right? From the conductor material that's making noise directly into the air, and it transmits therefore quite readily through that medium. Partial discharge detection, the other type, is where the defect is actually inside the insulating material. So it could be the cable insulation, it could be a standoff bushing or insulator, where when it was manufactured, there was a small void or defect inside the insulating material, basically a little air bubble, right? And on 5 kV and above equipment, what can happen is that arcs can actually occur inside of those voids in the insulating material. They will slowly eat away at the insulating material from the inside out. As they arc, they will degrade the material. Eventually, they can cause a failure to ground, all right, or a face-to-face failure. Those types of defects, they make ultrasound noise. They make noise in that 40 kilohertz range, but because it has to transmit through the medium of the insulator and then transmit from there out to the air for us to hear it, the level of sound that's made and that gets transmitted into the air medium that we could pick up is very low. So we use a different technique called transient earth voltage detection, where we're actually looking at voltages to ground that get induced in the skin of the electrical equipment. So it's good for medium voltage transformers, it's good for medium voltage switchgear. It's a different technique, a different sensing technology that we're using in order to pick that up. Motor current analysis, our friends from PDMA are going to talk to that at length. So motor current signature analysis essentially allows you to look at different characteristics of the motor, both de-energized and energized. What are the voltage and current waveforms versus a normal parameter for a given motor, right? So it allows you to trend different data points, and from that identify rotor problems, stator problems, winding problems. All of these will have different signature patterns that will show up in your motor current signature analysis software. Ultraviolet is used also for detection specifically of corona, a type of partial discharge. Will also give off not just ultrasound, but ultraviolet light. So we can use a UV camera, which is at the opposite end of the spectrum from infrared, right? We're at the high end spectrum, whereas infrared is the low end spectrum of light. And we are looking for the optical visualization of corona with a UV camera. So it's something used by utilities to exactly pinpoint where a corona event might be happening, and by any large industrial customers that have their own medium voltage and high voltage switchgear. They may also use UV detection as a technique. And lastly, we should never discount our senses. All 5, right? When I visually inspect a piece of equipment, what am I looking for? I'm looking for signs of water ingress. I'm looking for dust accumulation. I'm looking for pests that may have gotten in, snakes, spiders, all kinds of other critters like warm places that electrical enclosures provide. I am also smelling the equipment. Is there an unusual smell coming off of it, that burning insulation smell or anything else that's strange? The smell of ozone, that smell you get after a lightning storm, right? That's something we can pick up with our senses. Some people are more in tune to it than others. My wife could probably smell it from a mile away. I'd have to be right beside it. That's men versus women when it comes to the sense of smell. So let's not discount that. And in addition, is the equipment vibrating strangely, right? Am I hearing anything in the audible range off of the equipment that sounds unusual? So I've walked past this piece of switchgear 100 times in my career here. Today I'm walking by and I'm hearing something. Could be a mechanical connection that's loose and is vibrating. It could be something that's changed on the load that's actually changed how the equipment is mechanically resonating. All right? So we listen for those things, we look for those things, we use our sense of smell, and you can use your sense of touch as well on the exterior of a piece of gear. If you do an IR scan and you see a hot spot on the outside of a piece of gear, okay, touch the gear too. How hot is it? It may be something funny going on. So all of those can be utilized. Now, what is it that we want to inspect? I usually tell people that the primary points of failure in electrical apparatus are where we transition from one conductor type to another. Where we go from cable to bus, we have a lug, we have a crimped connection. All of these suffer from the exact same potential phenomenon, which is that 2 dissimilar metals will have different coefficients of thermal expansion And as the load ramps up and down and those conductors heat up and cool down, they will expand and contract at slightly different rates, which will slowly over many weeks and months and years cause them to get looser. And as they loosen, you can now start to have a higher resistance of that connection, which will then increase the amount of heat that is given off by that connection, right? In proportion to the current squared, So it's, P equals I squared R. So over time, every electrical connection will, with thermal cycling, slowly get looser. How long will it take for it to get to the point where it's really a significant issue? That's always the question mark. So any point where we are transitioning, any point where you have a semi-permanent connection between two conductors is something that we want to inspect because it can become a thermal issue, and those thermal issues can very easily become ultrasound-based issues as well. So it can start to give off partial discharges. So that's what we want to look at. Now, if I have an electrical connection and I perform infrared, and I don't see anything unusual temperature-wise, and I listen with my ultrasound test equipment and I don't hear anything unusual, and it's medium voltage and I hook up my transient earth voltage detection and look for partial discharges that way. Nope, nothing there. Motor current analysis, it's a motor connection. Everything looks fine. Everything is within the normal parameters. I do a UV scan on my overhead. Everything's good there. I visually inspect it. It's clean. There's no water. There's no pests. There's nothing going on there. I don't smell anything funny. So what can I do as the maintenance manager responsible for that asset to make it any better? Is there anything I can do? No. I got a no shaking head. So just because it's, what is this, November, and we've got our Thanksgiving shutdown coming up, in a week and a half, should I do anything to that piece of equipment just because I've got that scheduled outage? No. Why would I? Why would I go in there and tighten anything or clean anything or generally disturb that equipment in any way, shape, or form if there's no indication that there's any kind of a defect, right? So I go to the doctor. I'm 50 now. Happy birthday to me. A couple months ago. I'm 50 now, so I go to the doctor every year because my wife makes me, like most men. And the doctor checks my blood pressure, and he takes blood and checks for PSA and cholesterol, and all the other weird things that they run through that annual sample, and they check my blood glucose levels, all that good stuff, right? And he comes back to me and he says, nope, you're good. Come back and see me in another year. It's the same thing with our electrical assets. Now, if he sees something unusual, he might say, you know what, come back in 6 months instead, or come back in 3 months instead. Same thing, if I see something unusual here, doesn't mean that I'm necessarily going to take a shutdown, that I'm going to disturb that equipment. I may just want to monitor it more closely and see if that unusual data point trends negatively in a tighter interval. All right? So instead of coming back for my annual inspection a year from now, I'm going to come back in 3 months or 6 months instead, just to see if it's getting any worse than what that initial indicator of something funny is. Right? Now, the one thing he's not going to do is he's not going to order exploratory surgery on me, especially if everything checks out fine. He's not going to say, you know what, I think we should go in and remove your appendix just as a proactive measure. No, I don't think I want to do that, doc. And this is what we're asking people to do. We're saying, oh yeah, it's November, it's the shutdown, let's go in and tighten the crap out of everything. Let's go in there and do surgery on our switchgear. Is that smart? Not really. Doesn't make a lot of sense, and that's really what calendar-based maintenance is telling us to do. Now, if I did detect a problem, all right, that, as I said, doesn't necessarily mean I need to take immediate corrective action. It may just mean that I need to step up the interval at which I do future inspections. Because the way that electrical assets fail is relatively slow, all right? And we have what's called the PF curve that kind of goes over this. Now, there were 4 studies that were done that sort of derived this concept of the PF curve. The first 2 were done by the airline industry back in the 60s and 70s when they migrated from the original jet aircraft, and they moved to these wide-bodied aircraft, all right? And Prior to that, all maintenance that was required by the FAA on aircraft was derived off of millions of passenger air miles. So you looked at how, for replacing the windshield of an aircraft, it was a certain number of million passenger air miles, and then you just replaced it, right? For doing a full-blown refurbishment of an engine, it was a different number. For, changing the landing, the struts on the landing gear of the aircraft, it was a different number. And when they went to these larger aircraft that had 2 or 2.5 times as many passengers on it, the airline industry went, well, wait a second. That's going to mean we have to replace everything twice as often or even more? That doesn't make sense. We need to do some study on this to understand and put some legs to an argument back to the FAA about how we could change our practices so that it doesn't bankrupt us, right? Because if it goes off millions of passenger air miles, this is not going to work for the aircraft industry going to these larger aircraft. So they commissioned 2 studies. The original one was Nolan and Heath. The second one was the Broberg study. And both of these sort of came up with the same conclusions. And then the US Navy started looking at this as they migrated to sort of this nuclear era of vessels, and they needed to think about maintenance and reliability differently with that type of infrastructure simply because of the implications of what could happen in a failure, right? So there was all of these studies kind of were done thinking about this, and what they came to was the conclusion that collectively, only about 11% of the failures of assets, whether these be mechanical or electrical assets, have to do with the age of the asset. So stuff doesn't wear out like we think it does and fail. What really happens is that almost 90% of the time, the failure has absolutely nothing to do with how old the asset was. It's random. All right? It's infant mortality, it's random, it's its initial break-in period. Now you'll notice the biggest number here is infant mortality, 68%. That sounds crazy big. But included in infant mortality is every time that you do a physical maintenance intervention on a piece of equipment that resets the clock, and a failure that happens right after that is called an infant mortality failure. So it's not just when you bought the asset, it's after you've done a maintenance task on the asset. If it fails shortly after that, that goes in there. So what that tells us is that we're actually maintaining our way to unreliability. We're causing more failures than we're preventing. So they came up and said, okay, now these studies all came to essentially the same conclusion. And the gist is that if you are making your bets on maintenance on your asset infrastructure based on a calendar-based program, we're just going to do it because it's November, right? Or every June we do this, right? During that shutdown period. If you're making your bets like that, you are wrong at least 75% of the time, possibly more. Okay? It's this idea of it wasn't broken, but we fixed it anyway. Oh yeah, and while we were trying to do that, we actually did break it. That's what calendar-based maintenance is all about. Now, I come from the electrical switchgear business, right? I spent over 21 years working for one OEM and a little time working for another one, and I wrote operation and maintenance manuals for low voltage switchgear, for capacitor banks, for medium voltage equipment, for inverters, for active harmonic filters. I wrote manuals and was involved in the process of developing products like that at the OEM level. And I will tell you that calendar-based maintenance makes sense for one piece of your electrical infrastructure, that's your circuit breakers. You should follow the OEM's guidance for current injection testing and mechanically operating the units and lubricating the apparatus of the switch, et cetera, because they've actually done the research and spent the time and they understand how those devices work. They do not understand how a passive electrical connection loosens up over time. In their O&M manuals, they will write things like, go and tighten it every 12 months. It is based on absolutely this much science. 0, none, right? In fact, the guy that writes the manual, in that case me or one of my staff, would probably say, well, let's make a recommendation. We need them to tighten it every once in a while. They should do it every 24 months. And we would write that into the manual. And then who's the last person that reviews the operation and maintenance manual before it gets published by the OEM? Oh, you wish. No. No, the lawyers. The lawyers are always the last people to review any document written by the OEM. So what does he do? 24 months? Nope, 12. We got to cover ourselves. We got to make sure that, we tell these people to maintain this stuff in an interval that's going to cover our risk. It's all risk abatement, right? Those numbers that they put in those O&M manuals, they mean nothing. And there's some guys from Schneider who were here. Boy, I wish they were in the room because, they still write manuals that way. That's the reality. But it doesn't really reflect the reality of what you should be doing. And in fact, we're doing a disservice to our community of practitioners of asset management. So the gist is we have all these technologies, all these techniques, infrared, ultrasound, visual, etc. All of them will give us warning signs that something's not right in this equipment. It's not mint. It's not the way it was the day we commissioned it when it was perfect, theoretically, right? Sidebar. So you specify the equipment, you do all your research, you buy really good stuff at the end of the day, and then you hire the cheapest contractor you can find to install it. Cautionary tales abound about that practice. Everybody's seen it happen, right? We had a shipping split. They were supposed to put it back together again and torque the bus bars to a certain level, and they just never did. And it could run like that actually for years, but eventually it's going to cause a problem. So there's all kinds of things that can happen. Anyway, coming back. Early warning signs, they will get more distinct the further you go down this PF curve. P meaning that something has changed in the equipment that is a problem, which eventually, if left unchecked for long enough, will result in F, functional failure. And the longer I delay taking a corrective action, the higher the cost to repair is going to be. Why? Because it will start causing more damage and more damage and more damage to that component, and eventually it could cause damage to adjacent components, all right, or adjacent equipment if it's really bad. So the longer I let something go, to the point where it gets hot to the touch, makes audible noise, and then what's the technical term? We let the smoke out, right? Hard to get the smoke back in once you've let it out of a piece of electrical equipment. It's hard to contain. So we don't want it to get to that point, but we've got all these technologies that can help us detect these problems early. Right? So first thing I might pick up, maybe I'll pick up some corona coming off a piece of gear. Corona by itself, not so particularly bad, unless you're running an AM or FM radio nearby, in which case it's going to drive you nuts because you won't get your signals through to the radio very well. Motor current analysis, you might not see anything. Maybe you got a slightly high resistance or something. You don't see anything thermally. Everything's within a few degrees. When you're looking at a circuit breaker and if it's a balanced three-phase load, the temperature should be same on all those connections into and out of that circuit breaker, right? There shouldn't be any huge variation there unless you've got a higher resistance connection on one phase. Now, if you've got a phase imbalance, that's a different story because, if you've got a 30% imbalance on one phase versus the other two, yeah, absolutely, there's going to be different level of heat seen on that one phase. So you kind of have to, look at what the load characteristics concurrent with infrared as well. So that's the one cautionary thing there. So if we let it go further down the curve, maybe we start to get, tracking inside that gear. Maybe we see a couple of indicators in our motor current analysis that are saying, oh, something not quite right here now. We're not in the red zone yet, but we are starting to see things that are definitely yellow, and we want to start thinking, okay, maybe we need to take a corrective action soon, or maybe we have to step up again that interval. Thermal patterns start developing, right, and other technologies too. And then lastly, if we let it go further, we could get to the point where we've got a full-blown arcing going on. Right, now we've got an intermittent path to ground for energy. It's not a full-blown bolted fault, but it's going to be if we leave it. So let's be careful. Again, thermal patterns get more distinct. We might see, that motor current. We're now seeing a couple of parameters that are in the red zone, so we need to take some corrective action there. So again, all of these are these early warning signs, and the value of any type of condition-based maintenance program is that we get to reset the PF curve. If we find the problem, we decide that it's now time to take corrective action, we get to reset the PF curve and put that equipment back into mint condition again. All right? And now we start all over again and we start monitoring again. Now, what assets do you worry about most? What technologies should you be deploying to check for asset health? And at what interval? Those are kind of the three big questions, right? So we go through an FMEA process, failure modes effects analysis, also sometimes called a criticality analysis. And this is a system that you need to think about for yourself. Create a point system, all right, that looks at how can this equipment fail, right? What are the modes of failure? Therefore, what technologies would detect those modes of failure? What happens to my process or my facility if this asset is to fail? What gets affected downstream, right? And electrical infrastructure, it's a pyramid. The stuff at the top of the pyramid takes out everything down below the pyramid, right? You know, that piece of incoming medium voltage switchgear or that main utility substation transformer, that 10 MVA transformer or 50 MVA transformer, it goes out, we are pooched. Everything downstream is out of operation. So think about the effect of failure. What happens to us, and therefore what's the potential cost of downtime, but also what are the potential environmental factors, right? Could we cause an environmental incident as a result of an asset failure, right? Could we be dumping untreated sewage water into the river as a water treatment plant? You know, could we be, having some chemical that, wouldn't be treated or stored properly or whatever, right? There's all kinds of things that we can look at. And the Houston shipping channel is a notorious example of what can horribly go wrong, when we have some kind of a catastrophic failure and our backup systems fail as well. What is the cost to replace that asset if it is a catastrophic failure? And what's the lead time to get a new piece of equipment in? Now, if it's something I can go to the local Gray Bar or Wesco and buy off the shelf, hey, I can have it here this afternoon if it's failed, right? That may be the case, but you got to understand that. If it's a 2 MVA transformer with a weird low voltage winding configuration, that might be a 12-week replacement item, right? What is the cost to repair? Because not every failure is catastrophic. It's probably like 1 in 5 asset failures are catastrophic where the asset needs to be fully replaced. 4 out of 5, we can figure out a way to repair it, maybe even as a temporary repair while we do get a full replacement. But, we can get things back up and running again. So you got to think about mean time to repair, mean time to replace, cost to repair, cost to replace. All of these become essentially a point system for each and every asset, and we give them a ranking of criticality, and the stuff at the very high end of that is what we're going to worry about the most. Now, we can also create it two-dimensionally as a heat map and say, okay, what's the severity of the failure and what's the likelihood of the failure? Because there are some assets that may have a very high severity of failure, but a very low likelihood of failure, right? So those ones have we'll have a different mindset about how we're going to do the condition and health assessments on those than the ones that have both high likelihood and high severity of failure. So we can heat map our assets and then decide what is our appetite. This doesn't want to play. Doesn't want to play. Okay. Appetite for risk. And the stuff in the upper right-hand corner, right, that may be 5% of the assets in your facility. And you might say, you know what, on that stuff, I am so uncomfortable with what happens when it fails and how much it's going to cost us when it fails that I might want to actually think about online monitoring, temperature monitoring, partial discharge monitoring, power quality monitoring, online everything. Give me data 24/7, on that asset so now I know exactly what's going on. The stuff in the lower left corner is the exact opposite. This is run to fail. I don't care. It fails, I go get a new one. It doesn't affect me. Nobody gives a damn. Nobody's going to lose their job over it. Doesn't cause big problems for us. And run to fail can be a strategy, but only if you've actually gone through this exercise and decided which assets that's an appropriate strategy for. If you're just doing run to fail on everything, that's not a strategy. That's just a mess, right? And when is a 122 40 volt lighting panel a critical asset in your facility? It's a trick question. Yeah, maybe. I usually say it's when it feeds the boss's office, right? That's when it's critical. Yeah, that's when it's critical too. Yeah, so so you got to think about what comes downstream from each and every asset and what happens if this asset fails. And you can absolutely have, assets that you wouldn't give a second thought to in most instances, but they're critical because of what's coming off of them, right? So absolutely true. What you'll find is that most of your stuff falls somewhere in the middle, right? And then once you understand the modes of failure, then you can say, okay, well, for that asset, the primary mode of failure is heat problems, right? So I'm going to do infrared inspection. Now, how often should I do it? 3 months, 6 months, 12 months? What's the right recommendation? Well, that depends on the asset type, right? And then you have to think about what's the interval of failure. How fast can something go from P to F on the PF curve? Now, if I think that it can go from P to F in 9 months, then I should probably inspect in 6 months, because then I'll catch it. I'll catch it early enough that I can take corrective action. Right? If I think it's going to go from P to F in 18 months, well, then an annual inspection's fine. So you got to think about that as part of the process to determine what's the right frequency of inspection. As long as your frequency of inspection is shorter than your interval of failure, you're good, right? And you know your assets, frankly, better than anyone else. So we think of this as a family. We call it critical asset surveillance technology. So it's all of these different techniques, and everything that we do at IRIS is to try and facilitate clients doing this data collection safely and effectively and efficiently. Now there's some standards, obviously, that we have to work inside of. So we have the three NFPA documents, the 70, which is the code. We have the 70E, which is the practices for how you maintain and work on equipment safely when you're in maintenance mode, when you're intentionally taking it out potentially of its closed and guarded state, its normal state, and you're doing something to the equipment that's taking it out of its normal. And then there's the 70B, which has some guidance around how often should you do different types of maintenance and condition-based assessments. So there's some good documents in there, and there's also guidance from NETA that say, okay, what's normal temperature variance, what's normal ultrasound. There's some good documents that exist that can be good reference points for you as well. Now the 70E, just like the National Electrical Code, it's on a 3-year revision interval, and so the 2018 edition came out. And the biggest change, I think, there was that they previously had this thing called the hierarchy of risk control, but it was almost like a footnote. Now it's become part of the core document, and it has kind of become mandatory that thou shalt follow this hierarchy of risk control when you're thinking about any kind of invasive maintenance task. The other big change that they made was that you actually have to plan for human error, which sounds nuts, right? How do I plan for human error? But it's really it's a risk mitigation technique. So when you are going through and creating a job safety plan, you have to think about all the things that we could possibly screw up. And if we screw up, how will we react? And have that baked into your plan. So it's essentially, a technique to make sure that you have thought through all of the potential ramifications of the task that you're about to ask people to perform, and that you've got backup plans in place in case something goes wrong. So the hierarchy of risk control has sort of 6 parts to it. And essentially the rule is do the first one first. If you can't do that for some reason, then and only then can you move to the second. If you can't do that, then and only then can you move to the third, and so on down the list, right? So it must be followed sequentially. First one is, can I do this task de-energized? That's the question you ask yourself. Can I perform this maintenance task de-energized? If so, if the answer is yes, then that's what you do. Stop. Don't go any further down the list. Do it de-energized. Take the shutdown, even if it's inconvenient, find a way, do it de-energized. Now, there are some things, condition-based tasks, that I can't do de-energized. Remember the light bulbs, right? I can't do infrared de-energized, I can't do ultrasound de-energized, I can't do motor current. Well, the one type of motor current I can do de-energized, it's a de-energized test, but I can't do the energized type of testing, obviously. So then and only then do you move to number 2, substitution, also called safety by design. Substitution, the question is, can I redesign the work task and or the equipment in such a way as to eliminate the hazard 100% without introducing a new hazard? All right, and that's a tough one. Can I redesign the equipment so I can eliminate the hazard and the person can conduct the inspection or maintenance task and I don't introduce a new hazard? In other words, redesigning the work task so that the guy climbs up a 20-foot ladder is probably not a good substitution example. Right? Because we've introduced a new hazard, a fall from height. So this is where most of what IRIS does fits in. So we have devices that allow you to redesign the work task, so you can do the infrared, do the ultrasound, do the visual inspection with the equipment closed and guarded. You don't have to do what this poor guy's doing. So that's number 2. And then you have the engineering controls, which is, can I redesign the work task in such a way as to reduce the hazard? Not eliminate, but reduce the level of hazard. So if I can't eliminate it, can I reduce it in some way? So this is engineering controls, permanent barriers, interlocks, special grounding schemes that reduce the available fault level on the gear, maintenance modes on circuit breakers that you turn that into maintenance mode and it reduces the available fault level. Well, it doesn't reduce the fault level, but it decreases the trip time, which reduces the arc flash incident energy level, right? So all these little tricks and things we can do to reduce the risk, but not necessarily eliminate it. All of that is engineering controls. The next one is awareness, which is warning signs, barriers, making sure you only have qualified personnel in the work area. Job safety plan comes into that. Energized electrical work permit falls into that as well as the fact that you're supposed to be renewing your single line diagrams, right? That's in there. And you're supposed to be on I think it's a 5-year schedule, you're supposed to be redoing your calculations for arc flash incident energy labeling and relabeling your equipment. That's baked into the 70E as well. Right, so all of that is this awareness piece. Then you have the admin portion, which is training, making sure that people have gone through the requisite lockout tagout training, CPR training, AED training, all of the different trainings that make them qualified personnel that you've documented, that you've retrained at the appropriate intervals, and that's documented as well. That sounds, and that sounds like a lot of work, doesn't it? And if you've done all of that stuff, then and only then can you put on your PPE and open the panel and do that task energized. That's what 70E is telling us. There's a lot of paperwork involved to get to this point now. So 70E's got some interesting language in it about infrared inspections. It basically says you can do infrared or ultrasound condition-based type inspections without the need for PPE, but not if you open the door of the panel, right? As soon as you open the door of the panel or you remove a cover of the panel, everybody's got to be in PPE. So it's got some very specific language about that that's baked into the 70E as well. Now I talk about safety and reliability as being interwoven together and inseparable. There's lots of ways that we interact with our electrical equipment. They're listed out here. I won't go through them all. But each and every one of these is an opportunity for something to go wrong. It's an at-risk behavior, right? Every time we ask somebody to do this, we are putting them at some level of risk. And so we worry about that. And every organization, if you go and ask them, who's responsible for safety in the organization? Everybody's responsible for safety, right? If not, boy, you're in big trouble if everybody doesn't say that in the corporate meeting with the plant manager or the CEO. You better all say we're all responsible for safety. Who's responsible for reliability? Anthony, he's responsible for reliability, right? It's one guy. Is that right? Are we really going to move the needle if only one guy is responsible for reliability in the facility? No, we're not going to move the needle at all. There's no way. We've got to make sure that our leadership, right, the plant manager, the CEO, the CFO, frankly, too, understand that safety and reliability are two sides of the same coin. Now, the data supports that. And this data is courtesy of Ron Moore, who Ron's a prolific writer, gazillion years of experience in the reliability field. And he has worked as a consultant with hundreds and hundreds of companies, and he's compiled some really interesting data. But basically what he's been able to show is this linkage between safety and reliability again and again and again and again. So here's one example where he's looking at a particular company where he's looking at asset utilization or equipment effectiveness, it's the same thing essentially, versus injury rates, right? So as our asset utilization goes up, our injury rates go down. Okay, that's interesting. As our reactive work orders go up, our injuries go up. Okay, now this is getting more interesting. So in other words, that means what happens when something breaks down unexpectedly in the plant? What does everybody forget about all of a sudden? Safety goes by the wayside. Why? Because we got a plant that's down. everybody better scramble and figure out how we're going to get this stuff up and running again. All those rules about safety being job one kind of become safety is now job two. Job one is get the plant back up and running again. And that's what this data is reflecting, is that cultural shift. Also, who's the hero inside the plant? It's the guy who can get the emergency breakdown back into operation again, right? Everybody gives him great hand of applause. Bob got us up and running again. He knows how to fix that piece of equipment faster than anybody when it breaks. Okay, but why is that? Because it's broken 5 times before, right? What we need to be celebrating is the guy who actually figures out what the root cause was and not just fix it, but improve it. Change the way that piece of equipment works, or change the way that we're doing the maintenance on it so that we're getting those early warning signs that something might be going wrong, and then let's fix it before it gets to functional failure. Right? That's what we need to be celebrating. That's harder to celebrate because we're celebrating things that didn't happen. How do we celebrate when something doesn't happen? Yeah, this is really hard, right? So that's challenging. It's a cultural shift, but we've got to start thinking about this in a different way. Correlation between PM and predictive maintenance, so preventative and predictive maintenance work orders versus injury rate. Now this makes sense that the more preventative work orders that we do, the more likely that we're going to fix these problems before they fail, and our injury rates go down as a result. And I think this might be the last one. Maintenance schedule compliance. So it's all fine and good to say we're going to do preventative and condition-based and predictive maintenance activities, but if we don't actually do them, it doesn't work either, right? So we've got to both have a plan and then have the discipline to actually execute the plan. Otherwise, things fall apart, right? And then injury rate versus reactive maintenance. Again, injury rates are going to go up as we're doing more reactive work. And then last one is cost effectiveness. So this is the one that gets the CFO's attention, where we go, you know what? If we have better asset utilization, we've got lower production unit costs, and our overall reliability is increasing as well. Oh, okay. Now this is coming straight to the bottom line. Now I'm getting it, says the CFO. So we've got to think about these two things as being linked. Now the other piece I say about electrical safety is that in the general population of all workers in the United States, including office workers and industrial and everything, they have this pyramid which basically says, look, if you've got 300,000 at-risk behaviors, which could be something as stupid as me stepping on this desk to change that light bulb. It's an at-risk behavior. There's an opportunity for me to do something silly, fall off, break something. Of that, we've got 30,000 near misses where I almost fall off, 300 recordable injuries where I actually did fall off and I have to report it and do paperwork, 30 times where I'm actually going to be off work for a while, and once where I hit my head so bad I died. That's the general population. In the electrical space, it is much more dangerous because the at-risk behaviors that we're asking people to do, that list that I showed earlier, they're all that much more dangerous. So it's more like for 10,000 electrical at-risk behaviors, we're looking at a fatality. So we need to think about safety in a whole different way than the general population of all workers do because of the nature of what we're asking our electrical maintenance personnel to undertake. DuPont said that a maintenance technician with 2 years experience doing reactive work is the most likely person to be injured. ExxonMobil, anybody from ExxonMobil here today? No. ExxonMobil reported that accidents are 5 times more likely when you're doing a reactive work order, essentially, right? So it all plays to the same thing. So everybody should be responsible for both safety and reliability, and we should be really looking at a statement which is more of a safety and reliability statement for our organizations, because they are the same. If you drive reliability, you will drive safety. If you ignore reliability, your safety numbers you'll never get to zero, right? Because you're in that reactive mode where you're 5 times more likely to have an accident. Okay, so what are these things that fall into the substitution or safety by design thing? Essentially, it's any type of what we call an electrical maintenance safety device. It could be infrared windows, ports for listening for ultrasound, ports for connecting, test voltage and current for power quality, for your motor current analysis, the MTAPs, they call them motor test access points. All of those are sort of things. And then lastly, the online monitoring piece as well. So you've got temperature monitoring, partial discharge monitoring, power quality, vibration. There's permanently installed vibration monitoring that's a fairly common thing now. So different types of windows for looking and listening to the gear. We make all kinds of different kinds, whether visual, infrared, ultrasound capable, either with a ultrasound little port that swings open that lets you listen into the gear. And then we have the other challenge is data collection, right? So now if we're telling you that we want you to go collect more condition-based data, how many people running an enterprise asset management platform like Maximo or something similar? So Maximo users, hands up? So several. So Maximo is very common. The challenge is, okay, I'm going to collect all this asset health data. How do I trend it? How do I get it into a system? How do I do the analytics on it? That's the biggest challenge, is we're telling people, go out to the piece of equipment and take some measurements. Now, how does the guy get that data back into your platform? Writes it on a clipboard, or are you using like a mobile app thing or anything like that, or is it just manual data entry back at a desk? 65% of the time it's manual data entry back at a desk. That's what the survey, there was a survey done by Reliability Web last year. That's kind of the numbers that they came back with. So that's a painful way, especially for millennials. They don't want to have to write something on a clipboard and go back to a desk and type it in. They want to do it in an app. Right? And frankly, so do I at this point in my life. I don't want to go do data entry at a desk either. And who's got a secretary or somebody else that they can delegate that to? Like no one, right? So there isn't another option for us. So the idea of an asset tag, we think of that as part of an online monitoring solution where you have to get the data into a platform that then is cloud-based, that's easy to use, and so we have some solutions around that as well. Temperature monitoring, also an option. We have some temperature monitoring and sensors. So for that top tier of assets where you want 24/7, asset health information, those solutions exist. They exist from us, they exist from OEMs, they exist from various vendors. And then we do some handheld test equipment as well. So you guys can check us out at the break. We can tell you all about the asset platform if you like. So there's a couple of things that we talk about. So there was a study done by the guys from Emerson where they looked at the effect of increasing the frequency at which they do condition-based inspection on electrical and mechanical assets. And basically they found that if they went from not doing any condition-based inspections to doing once a year, there was a 10 times increase in mean time between failure. Well, that's huge. That's massive, 10x. But if they went from annual to twice a year inspections, there was still another 2.3x increase. If they went to quarterly inspections from annual, it was a 5.1x increase. And this inherently, it just makes sense. The more often we inspect things, the more likely we are to catch the problems early in the PF curve and then able to take smarter decisions about corrective action. The other thing that was done was the IEEE guys did a study where they looked at the cost of replacing versus repairing with and without a condition-based program in place. And essentially, if the outside of this spider web is the full cost to acquire an asset new, right? So if you look at the transformer thing, it's the outside right-hand corner there. If you have a no condition-based program in place, it's going to cost you probably about 55 to 60% of the cost of that asset to institute a repair when it does fail. Versus if you have a condition-based program in place, it's probably about 25 to 30%. Right? Because why? You catch the problem earlier in the PF curve before that cost gets out of hand and you've caused secondary and tertiary damage to other components versus the one that had the initial issue. So it's the same with all those assets, and I think the average was like about a 66% decrease in your cost if you institute a condition-based program. So it is important also from a design perspective to work with your original equipment manufacturer. So if you're buying new transformers and switchgear and motors and everything else, think about the fact about how are you going to maintain these assets? How are you going to perform these condition-based assessments? And can you design in the means and methods to do that safely and efficiently at the time that you procure the equipment? Because 60% of failures and safety issues can be reduced by making changes in the design. But 80% or more of a facility's life cycle costs are also impactable by design. If you do not implement the ability to collect infrared and ultrasound data on your assets, and then you want to do that after the fact, how are you going to do that, right? Are you going to do it with multiple people, open panel, go through all the steps of the risk hierarchy, and put on PPE and open up the gear, that's a dangerous and time-consuming exercise. So we look at acquisition of assets from the perspective of what does it cost me when I buy it initially. That's all that piece of the iceberg that's above the water. That's, you know, the actual procurement cost. It's the research of what should I buy, designing it in the first place. Maybe there's witness testing that has to be done, getting it constructed and installed. That's 15% of what I'm going to pay for that asset over its life. Because an electrical asset, you know, it's probably a 30, 35-year design, but we do have assets that are 50 years old. Absolutely. And we're having to figure out how do we maintain them, because we can't get the capital budget to replace them. Nobody wants to approve that, but they'll let you keep running it, right? So 85% of the cost of anything we acquire today comes later. So how do we minimize that? Well, we minimize it by making it easy to do these health assessments, which then, you know, makes that data collection easy, but then it also drives our decision making about when we physically intervene with the equipment. So I'm not going to go in every 18 months and tighten everything. I'm only going to tighten things when I actually see something wrong. Right? I'm only going to take a physical intervention when something goes wrong, which also means I'm going to avoid all those infant mortality problems. That 68% of the PF curve is infant mortality, a lot of which is a result of me maintaining something and fixing something that wasn't broken in the first place. Right? So that's where we want to focus our activities, is trying to drive out some of that after costs. So summarizing, time-based, calendar-based maintenance is a bad bet. At least 3/4 of the time it's a bad bet. Probably higher, probably 90% of the time it's a bad bet, right? The only time, as I said, where I think calendar-based maintenance makes sense is on circuit breakers themselves, because the OEMs have done their homework and they can actually tell you what you should do, and I trust them with respect to those recommendations. All other recommendations that they make, I'm kind of like very skeptical about. Condition-based technologies can detect those problems. You got to understand what's the mode of failure, what's the effect of the failure, what technology should I use, what's the interval of failure, therefore that drives my interval of inspection, right? So we can use all those different technologies to try and detect those problems and correct them. Most of those have to be done energized, but and because of NFPA 70E's changes, we've got to be really careful about how we do those things energized. Safety and reliability are, again, two sides of the same coin. You cannot separate the two. They are so closely linked together that we must focus on reliability to truly drive safety. And then the safety devices obviously help you with the data collection and keep your personnel safe and make them do that stuff efficiently. So, you know, and the last piece is like this design for reliability and total cost of ownership. So get on the committee that's responsible for procuring the new stuff. Have your voice heard about how you actually intend and must maintain it in future, so that that can be embedded and baked into the design, right? You're buying new stuff, take the lessons learned, apply them to your new designs to make sure that you're getting something that you're going to be able to maintain for the next 40, 50 years.